We are continuing with our review. This is going to be for part 2, forces and Newton's laws. So it's got some things for you to answer. First thing it wants to know is types of forces. So there are 2 ways of looking at this whole types of forces thing. One way to look at it is the big 5. So we've got the gravitational force, the electrostatic force, the magnetic force. Oh, sorry about that. The magnetic force and the strong force and the weak force. Those last 2 are our nuclear forces. They only exist inside of the nucleus of an object. But what's really kind of important about these forces, these are all our fundamental forces. These are, everything is a kind of force like one of these. We don't use those when we're talking about physics problems all the time. The ones that we use a lot, the forces we deal with, are things like mg, that's weight. Now that is a gravitational force. So mg is how we calculate it. It's the mass of the object times the acceleration due to gravity. Sometimes we call that Fg, other times we call that weight. But here's the deal. Anytime we talk about the weight of the object, it's going to be the mass of the object times the acceleration due to gravity where the object is. That's the only way we calculate it. That's why I like to write mg all the time. It tells me exactly how to calculate it. I take the mass in kilograms and I multiply it by 10 meters per second squared, and then I have the weight. We also have tension. Tension is a force that only pulls. Anywhere you see a string, we're going to be dealing with the tension force. We also have friction. Frictional force opposes the motion between 2 surfaces. And then we have the normal force. The normal force is a surface force, and it's normal because it pushes at 90 degrees. These are the 4 forces that we're going to deal with probably more than anything else. So when we do free body diagrams for a problem, these are the ones that we're really concerned with. All right, so we also want to define Newton's laws. You can draw your pictures for that later. But Newton's first law says that for an object in motion, it will remain in motion at a constant speed in a straight line unless an outside force acts on it. That's what you get from a book. The way I like to say it is that objects resist changes in motion, right? So if something's moving in a straight line, it's going to continue moving in a straight line. If it's at rest, it's going to stay at rest. This tendency of an object to resist a change in motion is called inertia. And the other thing that's important is that inertia is the same thing as mass. And so what this says is if the net force is equal to 0, the acceleration is equal to 0. That's all the first law. It means objects want to move how they're moving and not change, either at rest or in motion with a constant speed at a straight line. In order to change the motion of an object, we need a net force, which is what the second law is about. For the second law, what that really tells me is that forces cause acceleration. Forces cause changes in motion. And so acceleration is the net force acting on an object divided by the mass of the object. That little E symbol stands for sum or net. So it tells me the total force acting on an object. M is the mass of the object. And so the equation that we get is that the acceleration is net force over mass. The net force is the thing that causes acceleration. Mass, from Newton's first law, is the thing that resists acceleration. And then there's the third law. The third law, I think, is the trickiest one to deal with. For the third law, it says, it kind of defines a force for us. It says a force exists as an equal and opposite pair between 2 objects. The easiest way to look at that is to say, if I push on the wall pushes back on me with equal and opposite force. And these forces between two objects, and this is what's really important about this, forces between two objects are going to be equal and opposite. So we're going to go back through these laws again with these questions. The first law is often defined as the law of inertia. So we're going to define inertia. Inertia is the tendency of objects to resist changes in motion. The other way to define inertia is just to say mass. So if I want to change the motion of an object, if I want to accelerate the object, what I need is an unbalanced force. So the natural tendency of an object at rest is to stay at rest, because the natural tendency of all objects is to continue doing what they're already doing. So the natural tendency of an object at rest is to remain at rest. Same thing, the natural tendency of an object in motion is to stay in motion. Objects resist changes in motion. That's the big deal there. What relationship exists between acceleration, mass, and force? Draw two graphs showing these relationships. It's Newton's second law. Newton's second law says acceleration is force over mass. So if I do acceleration versus force, they're directly proportional. That's what a graph like that looks like. They're proportional to each other. If the force goes up, the acceleration goes up. The force goes down, the acceleration goes down. That's directly proportional. However, between acceleration and mass, they're inversely proportional. That's because mass is in the denominator. Now, what that means, move like that. If the mass goes up, the acceleration goes down. The mass goes down, the acceleration goes up. That's what inversely proportional is. F. Whenever a force is exerted on an object, what does the object do to the thing that exerts the force? This is third law. This is Newton's third law. So it pushes back with the exact same force. It exerts the same amount of force back on the object. That's the third law. All right, so now we have some example problems. This is going to be a guy in an elevator. So a man stands in an elevator on a scale at rest. This man has a mass of 100 kilograms. First question, what's his weight? Well, I know that the force of gravity is equal to mass times the acceleration due to gravity. Mass, acceleration due to gravity. I know that this man's mass is 100 kilograms. The acceleration due to gravity is 10 meters per second squared. So the weight of the man is 1,000 newtons. Draw a free body diagram showing all the forces on the man while he's at rest. Oh, 1,000 newtons. So that dot is going to represent the man. Pulling down is weight. Pushing up is the normal force from the scale that he's standing on. To find his net force is 0 because he's at rest. His acceleration is 0. He's not moving. There's no acceleration. The other way to look at net force is to add those two forces together. One's up, one's down, so one of them has to be negative. What normal force is exerted on the man while he's at rest? So we're going to use those two equations, the fact that because he's at rest, the net force is equal to 0, and the net force is the forces added together. So when we do that, we're going to set the normal force minus the weight. That's the sum of my forces. One's up, one's down, so one's negative. We're going to set that equal to 0. So if we solve for the normal force, it's equal to the weight, which we said was 1,000 newtons. So if the man's at rest on the scale, the normal force is equal to his weight, it's 1,000 newtons. And just to reiterate, that's the net force. That's adding those two things together. It's all the forces added together. The elevator now accelerates upwards and the scale reaches 1,500 newtons. Now we're going to draw the new free body diagram. He still has his weight acting down on him. That hasn't changed because he hasn't gone to a different planet. And the weight hasn't changed because he still has all his arms and legs. I haven't removed any mass. And now the normal force is up. And because the normal force is bigger, we're going to accelerate up. So if I want the net force acting on the man, I'm going to add my forces together again. We're going to make the normal force positive. We're going to subtract the weight. And we know both of those. So it's going to be 1,500 newtons for the normal force minus 1,000 newtons for the weight, giving me a net force of 500 newtons. Calculate the acceleration of the man. I also know that net force is equal to mass times acceleration. The net force we just found to be 500 newtons. The mass is 100 kilograms times the acceleration. If we solve for the acceleration, we get it to be 5 meters per second squared. Now, part G is just a kinematics question. How long does it take him to get 35 meters above his starting position? Well, he's going to start from rest, so the initial velocity is 0. The acceleration is 5 meters per second squared, and the displacement is 35 meters. I want time. The only equation that has all 4 of those things in it is the third one. Delta x equals v initial times time plus 1/2 at squared. V initial is 0, so it crosses out. So delta x, 35, is equal to 1/2 the acceleration, 5, times time squared. So we multiply both sides by 2 to get rid of the 1/2. We divide both sides by 5. And so I get t squared is equal to 70, 2 times 35, divided by 5. T squared is equal to 14, so time comes out to be 3.74 seconds. And h is just a repeat of g. We've got another example. Marcy pulls a friction block that has a mass of 3.5 kilograms at a constant speed of 2 meters per second. Using a force sensor, she finds the force that she pulls to be 28 newtons. Draw a free body diagram of the block and what's the net force on the block. So we don't have to do any work to get any of that. For our free body diagram, we have 3.5 kilograms as our mass. It's on a surface. Weight is pulling down. Normal force is pulling up. Marcy is pulling to the right, let's say, with that force of Marcy. And friction's pulling backwards. Now, here's the important part. I know her force is 28 newtons. It tells us that she is moving the block with constant velocity, the constant speed. So that means that the acceleration is equal to 0. Anytime you see constant speed in a straight line, the acceleration is equal to 0. If the acceleration is equal to 0, then the net force is also equal to 0. So boom, just because they tell me that she moves it in a straight line at a constant velocity tells me that the acceleration is 0, that the net force is 0. Find the force of friction on the block. Well, if we look in the x direction at my net force, it's going to be Marcy's force minus the force of friction. That's how I add those two forces together. Marcy's force moves us forward, that's why it's positive. Friction pulls backward, that's why it's negative. But I also know that the net force is equal to 0 because we said there's no acceleration. So if I plug those numbers in, Marcy's force, 28 newtons, minus friction, is equal to 0. So I add friction to both sides. 28 newtons is equal to the force of friction. Now, Marcy's going to pull with a speed of with a force of 38 newtons, and I want the acceleration of the block. So we're going to redo our free body diagram. I got Marcy's force, 38 newtons forward and friction backwards. Note that the force of friction does not change when she pulls harder. So that's 28 newtons backwards, getting it from there. Still have the normal force, still have the weight. So I'm accelerating forward, so we're going to do the same thing. So the box accelerates to the right because the force is unbalanced to the right. I have more force pulling to the right, so we're going to accelerate to the right. So to do the math part of it, the net force is my forces added together. That's 38 newtons to the right minus 28 newtons to the left. My net force then is equal to 10 newtons. But I also know that net force is equal to mass times acceleration. So 10 newtons is equal to the mass, 3.5 kilograms, sorry about that, times the acceleration. So we divide both sides by 3.5, and the acceleration is 2.86 meters per second squared. Part D, same block, but now I want to know Marcy's force, and I'm telling you that the acceleration is 4.5 meters per second squared. So net force here is still Marcy's force minus friction, and it's going to be equal to mass times acceleration. That's what we've been doing so far, right? The sum of my forces, Marcy pulling me forward, friction pulling me backward, Marcy's force minus friction is equal to mass times acceleration. Well, I don't know Marcy's force, but friction hasn't changed. It's still 28 newtons, so it's Marcy's force minus 28 newtons is equal to the mass, 3.5 kilograms, times the acceleration, 4.5 meters per second squared. So we're going to add 28 newtons to both sides. We're going to multiply that out. So Marcy's force minus 28 newtons is equal to 15.75. We're going to add 28 newtons to both sides. So Marcy's force is equal to 43.75 newtons. Part E, still dealing with Marcy here. If she exerts no force at all, what's the acceleration of the block? Well, if she exerts no force of all, the net force is equal to just Marcy's force minus friction still, equal to mass times acceleration. But now Marcy's force is 0, friction is still 28 newtons, and it's equal to the mass, 3.5 times the acceleration. So we divide both sides by 3.5, and the acceleration comes out to be 8 meters per second, negative 8 meters per second squared. That negative sign just means we are moving in the opposite direction. We have an acceleration in the opposite direction. That means we're slowing down. Still more examples. We've got Umberto, the mass of 125 kilograms, standing on ice skates on a frictionless sheet of ice, facing his partner, Isabella, who's only 65 kilograms. Umberto pushes her and notices that he accelerates backwards at the same time that he pushes her. He's got an accelerometer, and he finds his acceleration during the push to be 1 meter per second squared. I'm going to say he's going positive. So why does Umberto accelerate as he pushes on Isabella? Well, according to Newton's third law, Isabella pushes back on him with the same force, with equal force in the opposite direction. So we want to draw a free body diagram of both dancers while Umberto's accelerating. So we're going to do Umberto on the left, Isabella on the right. Umberto experiences a force to the left from Isabella, so we're going to call it force I. Isabella experiences a force to the right, force Umberto. They each have weight, they each have normal forces, and that's what we've got for free body diagrams. So we want to know the force exerted by Umberto on Isabella. Well, they're the same forces. The only information we have is Umberto's acceleration. So the net force on Umberto is the same as the force on Isabella. So it's the mass of Umberto times his acceleration. We've got 125 kilograms times 1 meter per second squared. The force between each of them is 125 newtons. I can use this to calculate Isabella's acceleration. I know that her force is going to be the same as Umberto's force, and it's going to be Isabella's mass times Isabella's acceleration. So 125 newtons equals her mass, 65 kilograms, times her acceleration. So we divide both sides by 65, and that acceleration comes out to be 1.92 meters per second squared. After pushing Umberto goes backwards with a velocity of 2.5. Calculate Isabella's velocity. So for this, we have a momentum problem, right? This is momentum. What we know about momentum is that initial momentum is equal to final momentum. And the initial momentum of this system is 0 because they were both at rest. And the final momentum is going to be Umberto's mass times his velocity plus Isabella's mass times her velocity. So 0, the initial momentum, equals 125 kilograms times 2.5 meters per second plus 65 times the initial velocity. So we're going to go ahead and multiply that out. 0 is equal to 312.5 plus 65 times initial velocity. I'm going to subtract Umberto's momentum, 312.5, from both sides. That gives me negative 312.5 equals 65 times the initial velocity for Isabella, or Isabella's velocity. Divide both sides by 65, and her velocity comes out to be negative 4.8 meters per second. So to find her velocity, we just do a momentum problem where the total momentum is equal to 0. So they have to have equal and opposite momentums. Part F wants to know how long were they in contact with each other. This is an impulse problem. The change in momentum of one of the ice skaters is equal to the force on the ice skaters divided by the time that they were in contact. So for Umberto, the initial velocity is 0. The acceleration is 1 meters per second squared. Final velocity is 2.5 meters per second, and we want to know the time. We could also do this with kinematics. Right, so we use the first equation, v final equals initial velocity plus acceleration times time. The final velocity is 2.5 meters per second, equal to 1 times time, so the time is 2.5 seconds. Describe the motions after they lose contact. Well, after they lose contact with each other, there are no forces acting on them, so they continue to move apart with constant speed. Without friction, nothing is going to slow them down. Nothing's going to change their velocity. So these next few questions are going to be on momentum, impulse, and the conservation of momentum. We've already previewed that a little bit. So, 5. An 8 kilogram object moves at 5 meters per second and gets an impulse of 16. What's the final velocity? So to solve momentum and impulse problems, impulse is equal to mass times final velocity minus mass times initial velocity. We know a lot of that information. My impulse is 16. So that's 8, the mass, times the final velocity, which we don't know, minus 8 times the initial velocity of 5. So 16 is equal to 8 times the final velocity minus 40. We'll add 40 to both sides. So 16 plus 40 is 56. 56 minus 8v final. Sorry, 56 is equal to 8v final. We'll divide both sides by 8. And v final comes out to be 7 meters per second. Number 6, a half kilogram ball with a speed of 4 hits a stationary target. If momentum is conserved, what's the total momentum of the ball and target after the collision? So, if it's conservation of momentum, we're saying the initial momentum is equal to the final momentum. Initially, the only thing that's moving is the ball. Okay, that's the conservation of momentum. Initially, the only thing that's moving is the ball. P final is the total momentum of the ball and the target together, because that's what we have. Initially, only the ball is moving. It's the mass of the ball times the velocity of the ball. So that's 0.5 times 4. That's the initial momentum. And the final momentum we just want the total momentum of the system after the collision, so it's going to be 2 kilogram meters per second squared. It's not going to change. 7 through 9 have a cart moving to the right and a cart moving to the left. They're moving with those speeds, and they're going to hit and stick together. So I want the total momentum of the two-cart system after the collision. Well, if momentum is conserved, it's the same as the initial momentum. P initial equals P final. P initial is object 1 has momentum, mass times velocity. Object 2 has momentum, mass times velocity. And so that's my initial momentum, but since momentum is conserved, it's also my final momentum. So that's going to be 4 kilograms, mass 1, times 3 meters per second, plus 6 kilograms, mass 2, times negative 3 meters per second. It's moving in the opposite direction. That negative sign is important. That's equal to P initial, which is equal to P final. So I got 12 minus 18 is equal to P initial, equals P final. And so the total momentum is negative 6 kilogram meters per second. And wants magnitude, so it's just 6. The magnitude and direction of the velocity of the two-cart system after the collision. Well, now we're going to take that and set it equal to what's going on afterwards. Oh, and just as a note, the word magnitude means size only. It wants the momentum, just doesn't care about the direction. That's what it means when we ask for magnitude. So to find out what's going on after the collision, we're going to take P final and set it equal to, since the objects stick together, we're talking about their total mass times their velocity. So that's going to be negative 6 kilogram meters per second equals 10 kilograms. So V final is negative 0.6 meters per second. That negative sign means it's moving in the same direction as the 6 kilogram cart, or to the left. Negative sign means moving backwards or to the left. Then in this situation, what's conserved? Well, we don't have the same velocity afterwards, so that's out. We lose kinetic energy because we're kind of overall slowing down. Momentum is conserved, but force is not something that can be conserved. All right, that's part 2 of our review.